Planar film heater. Electric film heater is used to heat up the glass. Glass thickness is 8 mm and the film thickness is 170 nanometers. The glass size is 1 meter by 1 meter. The electric current value is 5 ampere DC current. Our task is to calculate the temperature of the glass. To be able to do so, we should first determine the draw heat power. I'm going to use QuickField simulation software to conduct the virtual experiment. First, I'm going to simulate a two-dimensional DC conduction problem and calculate the current density distribution and the draw heat power density distribution in the film. Then I'm going to run the thermal problem and calculate temperature distribution in the glass. Okay, let's start QuickField now. In QuickField, I create new problem, heater. Next, problem type is DC conduction. I'm going to simulate only a cross-section of the heating film and the electrode, so the model class is plane parallel. Length in some millimeters. Finish. On the left you can see the problem pane, and on the right is the geometry model editor window. You should draw the geometry model here. Or you can import the geometry model from the AutoCAD.exe file. In the DC conduction problem, I'm going to calculate the power density distribution in the film. So I do not need to draw a glass, I need only to draw the conducting parts. Let's draw an electrode. Insert shape, rectangle. This would be the insert point. The electrode width is 2 mm and the thickness is 2 micrometers, so 0.002. This would be the thickness of the electrode. Insert. Close, zoom to fit. Zoom in. And in fact, these parts are slanted, so switch to insert mode, straight line, and draw the slanted part. Here and here. Okay, now let's insert another rectangle. This would be the insert point. The film thickness is 170 nanometers. I need to convert this to millimeters, so times 10 to the power of minus 6 millimeters. And the width is, the glass width is 1 meter, but we can simulate a smaller region, let it be 3 millimeters. Insert. Close, zoom to fit. And I believe I need to add a small part here. Again, insert, rectangle, 170 nanometers, convert this to millimeters. This would be the insert point, and the width 0.5 millimeters. Insert. Now we have copper electrode. I do not need this line, and I do not need this line. We have copper electrode on top of the conducting film. Let's assign labels. Through labels, you can explain the geometric object's meaning and provide physical properties. Switch to Select Objects mode, click the object to select, and type in the label name here. This is electrode. And this is film. Also, I need to assign labels to terminals. Well, let this be the terminal where the electric potential is applied. B+. And here at this end, I will specify electric potential of 0. Okay, now let's provide physical properties for these labels. Double-click the label name in the tree. The electrode is made of copper with electrical conductivity of 56 megasiemens per meter. The film electrical resistivity is 12.6 ohm per square. We need to convert this to the volume unit. So I multiply this value by the film thickness, 170 nanometers. Convert this to meters, and the result is this value. Ohms multiplied by meters. In QuickField, you should specify the reciprocal value, the conductivity, Siemens per meter, and the reciprocal value is 467,000 Siemens per meter. Copy this, paste it here. Okay. Now for the grounded electrode, the electric potential is 0. And for the voltage electrode, probably I should move it to the left, to the middle of the electrode. So let's move selection to the left by 1 millimeter. Okay, now it's in the middle. So for this electrode, I'm going to specify the current density. I know the current. The current should be 5 amperes. But here I should specify the current density. Current divided by the cross-section area. So let's measure the cross-section area. If I select the electrode, I can get its length, and the module depth is 1 meter. So the cross-section area is 7.5 millimeters squared. I need to convert this to meters squared. For the electrode, 5 amperes divided by the 7.5 times 10 to the power of minus 6. Current divided by the area. Okay. Now the geometry model and the material properties are ready. Before I can run the analysis, I should build the finite element mesh. Just press this button and the mesh will be generated. It might take a lot of time to build the mesh in thin structures. This trick might help you to speed up the meshing. You just need to subdivide thin region into smaller parts like this. If you zoom in, you will see that now the regions are divided in the shorter parts. Now all I need to do is to remove unnecessary edges. I'd better add dividing edges here as well. Remove unnecessary parts. Now let's build the mesh. It will be generated much faster. Now if you zoom in, you will see the mesh generated. Now save all problem files and solve the problem. The problem is solved. Let's take a look at the results. Let's zoom in to see what we have here. This is the color map of the current density. The current density here is almost 0. And if I take a look at the right part, you will see again that the current density in the electrode is almost 0. And the current density in the film is, here at the bottom you will see the value, 2.94 times 10 to the power of 7 amperes per meter squared. You can use the local varies tool, click and get the exact value. This is the current density and this is the joule heat power. Let's adjust the field picture and take a look at the joule heat power distribution. all the power is dissipated in the film. There is no power dissipated by the electrode. So in our next problem we will not simulate the electrode. We will only simulate the conducting film. By the way, what is the power? It is 1.8 times 10 to the power of 9 watts per meter cubed. And let's check the current. I'm going to use the contour tool. The current flows in this direction, so I build the contour across the current path, follow to the integrals, and the current is 5 amperes as I have specified. Okay, let's move to the second part and calculate temperature distribution. I create new problem, glass. Next. Problem type is steady state heat transfer. I'm going to simulate only a cross section of the glass here. So the model class is plane parallel, model depth is 1 meter, and length you need some millimeters. Finish. As we have learned, the power in electrodes is negligible, so I'm going to draw only a glass. I do not need to draw the film as a body. I will use a heat flux boundary condition instead. So I insert a rectangle with the dimensions 8 millimeters, which is the thickness of the glass, and 1 millimeter. I simulate only a small part of the glass. Insert, close, zoom to fit. Again, switch to select objects mode and assign labels. This is glass. This edge is external side, and this edge is internal side plus the heating. Internal plus heating. And at this edge the heat flux is 0. In fact, this is the default boundary condition in QuickField, so there is no need to assign a label to this edge. Okay, now let's provide physical properties for these labels. Double-click the label name in the tree. Thermal conductivity of the glass is 1. External. At the external side, the convection boundary condition should be specified. The air temperature is minus 15 degrees Celsius, and the convection coefficient is 23. At the internal side, the air temperature is plus 20 degrees Celsius and the convection coefficient is 8. And here I should specify the heat flux. Watts per meter squared. Well, I've learned that the power is this value, watts per meter cubed. Now I need to convert this to watts per meter squared. Well, I need to multiply this by the film thickness. And this will give me, multiplied by the 170, 315 watts per meter squared. It's much easier to work with these values than with these values. Okay. 315. Open the label properties and specify the heat flux. 315 watts per meter squared. Okay. Again, I should build the finite element mesh, save all problem files, and solve the thermal problem. Here you can see the temperature distribution in the glass. At the internal side, the temperature of the glass is 6.7 degrees Celsius, and at the external side, the temperature of the glass is 3.3 degrees Celsius. Let's measure the flux at the external side. Use the contour tool, click to select the edge, integrals. This is the flux, and this is the surface area. Put it here. Let's make sure that our approach with the boundary condition works correctly. I'm going to simulate the glass and the film as is, as bodies. So open the geometry model, zoom in, switch to select objects mode, click the object to select, right-click, duplicate selection, displacement up by 117 nanometers, which is times 10 to the power of minus 6 millimeters. Let's zoom in. Here is the film edge here. Zoom in. Click and draw the edge here. Now at this edge I do not need the boundary condition. At this edge I specify the condition only the internal. There is no heating source there. And this would be the film. For the film I specify a thermal conductivity of 4 and the volume power is, this is the number. Put it here. For the internal I specify only the convection. Convection coefficient is 8 and the air temperature is 20. Build the point implement mesh, save all problem files and solve the problem. Let's take a look at the results. And the temperature is the same. At the cold side it was plus 3.3 and at the warm side it was 6.7. Let's check the flux value. Click here to select integral, and this is the flux value. And when we modeled the film as a boundary condition, the flux was this value. Film as a boundary condition, film as a body. So this way you can use QuickField to conduct virtual experiments and analyze different film heaters' performance in different environmental conditions. If you search for the Planar film heater on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the result pictures and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.